Hello and welcome again. In the next 3 or so weeks, we shall cover the last section of this course, which is time series. There is a little bit of maths involved here, and I shall skip most of it. For those who have the appropriate maths background, you might be interested in looking at the details. The other thing we'll skip here altogether is all the estimation methods. There are these things, of course, have to be estimated. You will find details in the book. Mostly you'll find things that are likelihood based. So you can look through those yourself if you wish. Let's start. Here is the contents. You can look at that again. So time series here, similar to what we saw earlier in the mixed model section of the lectures, is data that has some time element in it. The difference between what we saw earlier as longitudinal data is the time spent there is a lot smaller, maybe only a few points, 5, 10, 12 or whatever else, and the time difference between observations is not uniform, it's not the same. So you might have observations after 1 day, then the next observation after 7 days, then 5 weeks, and so on and so forth. Typically in medical trials, you might have observations, say, within a week, then after 3 months, then after a year, and so on and so forth. Here, the time span is much longer, and the difference between the observations is the same length of time. So there's some uniformity here. So you can read all this yourself, but here we've got this idea specifically that time series data is different from longitudinal data, although of course it can also be called longitudinal, and that is essentially the same thing in one sense. So here, the difference between this and what some other data forms is if we have other coordinates as well, so they're measured together at the same points in time, sometimes such data is called canal data. So you've got essentially observations over several variables. One variable is a response variable, and the others are coordinates here. And sometimes the other aspects of the data, along with time, are spatial. So some of the time these things include spatial elements, and then it's called spatial canal data. We shall deal only with the situation where we have univariate measurements over time. So you've got something that's measured over time, and that's all there is. There are no coordinates here, although you can see from straight away that of course time itself is a coordinate, and we can have other coordinates linked with the time variable, as we will see. Now, a lot of the time series data, because it's over a longer period of time, there's two things we expect to see there. Sometimes the time series by its nature is seasonal. So if you've got data, for example, measured over the whole year and several years, you expect there to be seasonal variations over the 2 or 3 years as the seasons change, the autumn, winter, spring, and so on, or the months. And often there's also a trend here. So there's some trend, usually upward, downward, depending on what's going on there, and also some seasonality. So, as an example, of course, the temperature in Perth daily temperature, we expect to have seasonality. You don't expect here to be much in the way of a trend, although if you look at this over a long period of time, maybe over a few centuries or so, then we have this idea of global warming. So you might see some upward trend. Otherwise, though, you'll find that such data will certainly exhibit seasonality, but not necessarily a trend. So the data we have as an example here is from the book by Cryer. You'll find the reference in the end, and the data will be online, and you'll be using this in labs as well. So this is milk data that contains milk production over 12 years, pounds per cow, and this is monthly data. So this is just the monthly data over the whole month, pounds per cow. This is US data, that's why it's pounds. So here's the plot of the data, figure 1 here, and this is all the R command that's in there, so you'll be able to read this data yourself and repeat the R commands. The two things you'll see straight away here is the seasonality aspect and the upward trend. But it's not a straight seasonality. In other words, it's not smooth seasonality. If I can blow this up a bit more, certainly you'll find here, yes, you've got seasonality for sure, but there are blips in the data, and these blips actually are fairly regular. So there's something here, for example, that you will find happening throughout the years. And the top end also, this one looks a bit different, the first one, but other than that, those bits look the same. There's something happening, there's some movement, and also there's a little bit of a that blip over there as well before it goes down and up again, that kind of thing. So we need to understand exactly what those seasonal components are and how they relate to the data itself. But overall, you can plot it fairly easily if I go back to the commands we had here. So the first thing we did in the commands here, after reading the data in, is convert that to a time series object. So this is by this command ts. So ts here, I've given it the actual variable under the milk that contains the responses I want, and I've given the start year, and I've given the frequency, which is monthly, so it's 12 monthly. So that is enough for this to turn this into a time series object. I would advise that you have a look to see underneath the milk TS what it now contains. Have a look at the data frame and see what it now contains. Otherwise, nothing serious there. I can plot the things, I can plot most other objects. You can see I can plot this milk.ts, this time series object, and I've got here the scales on the axis. I have made them a bit bigger here, so the C-axis character expansion, I've made them a bit bigger here so that you can see the labels as well as the axes. So the labels over here, these ones are a bit bigger, and the axes as well, the scales there are a bit bigger as well. So as we said earlier, you can see both the seasonality and upward trend here. The second data that we shall look at throughout this part of the course is this temperature in a car, in the cabin and the boot. And I'll put a paper online for you to look at this. This is interesting because usually this kind of thing in forensic science is used to determine the time of death of a body. Not a very nice thing, but still important from our point of view as statisticians and data modelers here. And so the extent of decomposition, depending on the temperature, can be used to work out the time of death here. So what we have here is the temperature in the boot and cabin of a white Ford, and this is measured every hour for 10 days. And if you look at the data over here, over the page, here it is. This is in the boot of a car, the white Ford. You can see certainly this is seasonality. If this is hourly data over the days, and this is over a few months actually, as you can see here, starting at midnight on 10th February, over a few days, not months. And so you can see the usual pattern you expect with temperature over the day, high in the day and then cooler in the evening, but not much cooler, still close to 20, at least in the 10 to 20 range. But inside the vehicle itself, it can go as high as 50, as we can see. And because this is February, it looks like the February this year got hotter over the month from 18th onwards. This is in the cabin. Sorry, this is the boot. And over the page, we have the data in the cabin. Now, interestingly, in the boot, the temperature was a bit higher later in the month. Here, this is actually high to start off with, but this is starting on the 9th of March 2008, so a little bit later. And you can see it looks like it starts off hot. This is when the cold spell comes in and brings it all down, then it goes hot again as it warms up. So this is interesting. In both of these, certainly you can see the seasonal component, but the trend is not so clear. Is there a trend of some sort? And the question here is going to be, because the trend isn't clear and it may not be something like a linear trend, the question is, how do we actually model the trend? So, as we said here, typically in that case, but in this case with the temperature data, we certainly see seasonality, and there's some trend. And how, as I said, the question is how we model the trend and the seasonality. So typically you will find in time series data both of these things are seen, or at least seasonality is seen. Sometimes if the trend is seen, you've got very random noise around it here. So, from our point of view, we need to model both these. And there are two sorts of models we can look at. We can use the usual regression or linear model as we had before. Now, we do know that we've modeled in the past in this course the heterogeneous variance and also the correlations in data. So both of those could be used for this kind of data. The problem here being we know that we can fit a linear model of some kind, but we will still need to take care of the correlation in the data and maybe some heterogeneous weirdness as well. And the other method is what's called the Box-Jenkins models here, which is a different kind of model altogether. Nothing I would expect you to have seen before, so we'll develop that and look at this as well. And both of these can be conducted very easily in R, and both of these can be used for any data we like. The question of interest is going to be which of these types of models is the better model for a given data set, and which one is better at predicting as well as the fit. So let's move on. Now, the linear model as we know it isn't so difficult. We've seen this before. We have some response variable here, which is called the dependent variable, and then you've got the covariates or explanatory or independent variables here, the x's here, and the relationship here essentially is yi is equal to beta naught, the intercept, plus beta 1 x1i, beta 2 x2i, and so on until beta p xpi. So the I is indicating the ith observation. We can use t here instead because it's going to be time, and epsilon I is the error term. And as before, we expect the epsilon I to be normally distributed with some constant variance. If the variance isn't constant, we can model it. And we're also assuming here that the correlations are non-existent. In other words, the residuals or error term is uncorrelated or independent. So there are these three conditions: the independence or uncorrelatedness, the normal distribution, and also the constant variance. And of course we can estimate these, and then the fitted value y hat is given by what we get when we put the estimates of the parameters in there. Residual is the difference between, there's a plus here which is not right, annoyingly, should be the observed minus the fitted, and so the sum of residuals will be 0 because of how the modeling works here. And so that clearly shows you to start off with the residuals aren't independent. But the thing is, the question is going to be whether they are going to be uncorrelated enough for us to be able to see what's going on here. So model assumptions have to be verified. So we know no matter error comes from looking at the QQ plots, and that should not be very different from a straight line. But then we can also check for the constant variance and the appropriateness of the linear model, as well as correlation here. So how do we check for the constant variance? We look at the loss of residuals against fitted values to see if there are any patterns in there regarding a change in spread, and if there is some other pattern there that indicates some non-linearity or some other model, we can then look at the appropriate models here instead of just a straight linear model here. Now, as we saw here earlier, the problem here is that certainly in the time series situation, the data will not be uncorrelated. Looking at temperature, if we have a hot day today, you expect it to be hot tomorrow as well. Although, of course, it can suddenly die down, as we saw in the data earlier, but you expect some correlation there. And so time series data does exhibit these correlations. And we can pick out these correlations here by looking at the autocorrelation function. Now, in the case of the linear models, we saw something similar. We did see the serial correlation, autocorrelation in there. Here, there's two things we can look at: the autocorrelation function and also the partial autocorrelation function. And I'll explain what these means as we go through here. And model parameters are usually by least squares or by maximum applicable. Again, as we saw earlier, we can include categorical variables in the model here. And so we do, we set those variables with the particular levels, and then usually we have one as a reference level which doesn't appear in the model. The other levels all appear in the model. However, we do know that the intercept weight may not always be interpretable depending on the range of data. We can also set the intercept to 0 in the model explicitly by subtracting the 1 or 1 off from the model formulation. And then we have each of the levels of the categorical variable available in the model. That is sometimes useful because we may able to then see exactly how each of these categories contributes to the response. In our data, we certainly want to estimate the cyclic components. So if you look at the milk data, for example, we certainly want the cyclic component. So We can define indicator or dummy variables for this purpose, so that we have one level corresponding to each of the cyclic components. And in the record, exactly one of these indicator variables is non-zero, and the other will take a value 1, so essentially, so it will be 0-1 situation. However, in the case of something like the data we have for the milk data, we can set something as a character variable, or a factor if you like. So to start off with, we'll declare the year here. Now we know the year goes from 1962 to 1973, so we've got year here, and this repeat 12. Repeat each 12 times, and what we're going to repeat here is 1962 to 1973, so you get 12 lots of 1962, and so on and so forth. And of course the reason being here that I can then define myself a length variable, and there's 12 months altogether, and the length altogether will be 144. Each of these will be repeated once only, and then the whole set will be repeated an appropriate number of times to make up the 12 years I'm looking at here, 144. So you can see I'm going to get January, February, March, all the way till December. That is one set, and then another set, and so on. In other words, the whole thing is repeated 12 times. And this is ordered because I want this ordered, and I will set this ordered in the sense I've got the thing, January, February, and so on, because I want to maintain that particular order. So here also I require, if I'm going to model a time trend, then I require a variable that just stores the time points in there. So I've got these things all set up there. Now, you will find I won't be allowed to include all those in the model, so I can't, for example, use year as well as the month and the time together. Here's my data frame that combines all these things together. And here's my linear model. I've got time, which is my time variable 1, 2, 3, 4, and so on to fit the trend. I've got month, which is the cyclic components, and the -1 here, of course, removes the intercept, so I'll be able to see all the months in my model. So here's a summary of the fits. You can see what's going on here. I've got a time trend, a linear trend in time. We can discuss later on whether the linear trend is appropriate or not. Then I've got the monthly components, and all of them, of course, are very, very strong and significant. What I can see here, as far as the months are concerned, is that it looks like the highest month is about March, around here, around sort of 3 or 4 months there is about 130 and so on, about 136 even, and then it drops off a little bit. And of course this is US data, so their spring is our autumn, so April, May, June is their spring, and you can see there the volume of milk there is large, and then as they near the autumn and winter, September onwards, it starts going low, and it's low again throughout January and so on. February is quite low as well, probably the coldest month, and suddenly in March it goes up again. So that is not unexpected. Now on the face of it, this looks like a very good model because you've got all the variables are significant. If you look at r squared multiple r is actually equal to 1, and the residual standard error in this case is only 19. Now if you consider that compared to the actual data values, which go into several hundreds, if you look at the plots, if I can go back for a second, you'll find the plot of the milk data indicates values about 1700 or so maximum from 1300. So that means a residual standard error of 19 is not so bad at all. However, if you look at the residual plots on the next figure here, let's see what it looks like here. There's a plot of residuals. The first plot here, just points here, doesn't seem to do much, doesn't show much in one sense. But if you look at the plot, this is fitted versus the residuals, residuals versus fitted. If you look at residuals versus time, and it actually join them by line, as you can see here, this makes sense because there is some order in the data here, time order. It mightn't look like much, but there's certainly a peak over here. And if you look carefully, you'll find sort of this kind of pattern occurring here. This kind of pattern occurring here. So there is something happening here, as we know, because of seasonality, we expect something to happen here. So that is just the first foray into this area, fitting a linear model. You can see it fits fairly well, but can we make my model better? Now, there's a bit of covariance here, which I'm going to skip entirely. For those who've done the right maths, this will be easy. For those who haven't, I'm not going to teach you this stuff. This is only for the interest's sake, for those who are interested in this. So I'll just go through this very quickly, and I won't look at any details here at all. All done there. I want to take a look at these two things, which are the autocorrelation and partial autocorrelation functions here. And again, there's quite a bit of maths here, because these things are defined mathematically, and you can calculate them for particular models. But I won't do that in detail. I'll just look at the main results here. So again, I'll skip over this very fast. I just want to take a look at the main result from here. The second thing that is also going to be covered is this idea of stationarity. Essentially, stationarity means, what this means is no trend. In other words, the data is flat. It may have lots of squiggles and lots of variation, but the overall trend is zero. It's fairly flat in that sense. Again, I won't look at the details over here. None of this is important for us. What I want to take a look at is the kinds of processes we'll be discussing later on. So there's something called an autoregressive process. We have seen this before in the first part of the course. The idea here is that I have the data yt here, and I'm running a regression of yt on its own self, but lagged in time. So I'm looking at the value at the previous time point, then 2 away, and so on until I get to p away. And then there's the usual random error term here. So I'm regressing yt in itself, saying that what happens today depends on what happened yesterday and the day before, and so on and so forth. Now usually the number of legs we require are reasonably small. Sometimes 1, 2, 3 is all it takes here. And this is the kind of model we'll be fitting as well. So we want to know here, for the AR or autoregressive process of order 1, when I've only got one time lag, what is the correlation here in this case between those yt and yt1? What is the autocorrelation of this particular model? So the first order AR process, the main result I want to take a look at is this, that I have here, the process itself is just simply this, yt is some number phi times yt minus 1 plus the error term. I'm scaling it a little bit. The main idea here is the autocorrelation function here is just phi to the k. So if I'm taking a look at autocorrelation at lag k, so between the yt and yt minus k, t legs away, then it's just phi to the k. In other words, it dies down exponentially. So if phi, for example, is a value between 0 and 1, it is just going to go down exponentially. If phi is negative, what happens is it alternates. So the kind of thing I'm looking at is this. If it's just positive, it will be dying down slowly this way. If it's positive and negative, then similarly, but it will be alternating here. It will still be reducing, but alternating. Yeah, that's what's going to happen there. So that gives us some form of the function for the autocorrelation function for the autoregressive processes. There's something called the partial autocorrelation. The point here is that if I have yt and yt minus 1 and yt minus 2, if, for example, these two are related, then so are these two. And I might actually find that yt and yt minus 2 have a correlation, but only because this is in the middle has a correlation with both of them. So if I can remove the effect of yt minus 1 and then work out correlation between yt and yt minus 2, that will be interesting. And that's what this does. So for the AR1 process, what we find here is that all the autocorrelations here are 0, except for the first one. This is one defined by one convention. So between yt and yt minus 1 for the AR1 process, there's a correlation. With yt to yt minus 2, no, there isn't anything. After you remove the effect of yt minus 1, there is no effect further. So the interesting thing here is that the autocorrelation function dies exponentially, but the partial autocorrelation function has only one non-zero value. Everything else is 0. So we can use this for model identification to work out what kind of model is appropriate. So let's take a look at some plots here for the AR1 process. And I'll draw a line here for the moment. So AR1 process here, figure 4.1 shows what's going on here. Here's figure 4.1, and I'm going to code there, you can look at this as well. Here is the actual process itself. There's no trend here. It's just a straight AR1 process. What you find here is, as we said before, the model is going to be, according to the equation there, we got yt is 0.7, yt minus 1, and then plus the error term. So the autocorrelation should go down as, well, when there's no leg here, it'll be 1, but then 0.7 squared, yeah, that'll be 0.7. That's going to be 0.7 squared, and so on. It dies down exponentially. And the partial autocorrelation only has one significant component. Everything else is 0. Now, significant here essentially means, you see this 95% confidence interval bars, right? So that means that the only non-zero value for the partial autocorrelation function is at leg 1. And that indicates or identifies for us the AR1 process very easily. Now, going back here, I've got this thing about difference equation, and these difference equations are important in a lot of the discrete kind of problems we face in the future. Again, I will look at the details here. I'll leave this for you. For those who have the right background to look at it, and you can ask me questions afterwards. So I'll skip all of that. Again, for those who are interested in the maths and have done some of the maths, you will find here this thing called the Fibonacci series. And the Fibonacci series essentially starts with a value, repeats the value, and from there it's found, the next value is found by adding the next two previous ones. So this sequence here, once I start with f1 equals 1, and the next value is 1, and then I sum these, I get 2, and sum the previous 2, I get 3, sum the previous 3, I get 2, I get 5, then I get 8, sum the previous 2, I get 13, and so on. And while it starts off very small, it blows up very fast as well. Now, this kind of series I have an explicit value for. I can find the value explicitly by a formula like this. And for those who may be interested, this particular ratio here, the 1 plus root 5 over 2, is called the golden ratio, and it is quite interesting in geometry. Many things that feature this kind of ratio in themselves have some aesthetic appeal to them. And you can look up this golden ratio on Google and see what it actually means. If I go to the second order AR process, then it's a bit more complicated. And again, I won't look at the details here. But in this case, what I'm interested in is the plots again. So for the AR2 process, what you'll find is, while looking at the plots, first of all, the process itself, and here is the simulations. You can find the equation from this one here. Not so difficult. I have yt equals 0.6 yt minus 1 minus 0.8 yt minus 2, and then plus my usual error term. Now, the process itself looks okay. It's stationary. It looks fairly stationary and flat. As far as the AR, the autocorrelation function is concerned, you find because it's an AR2 process with a negative coefficient, there's some alternation in the values of the ACF. The first, of course, is always 1 because it's like 0. This is the positive, negative, negative, positive, positive, negative, positive, and so on. It seems to fluctuate a bit more here. There is no clear pattern there that leads us to anything that identifies this as an AR2 process. But if you look at the partial autocorrelation, then the first two legs are significantly beyond the 95% confidence bounds. And so in the AR2 process, we find that the first two partial autocorrelation values are bigger than 0, significantly bigger than 0. In other words, the first two are significant. And that identifies for us an AR2 process. Here is an AR5 process, and the equations there much more complicated. The plot still looks similar. It still is very flat with some blips here and there. If I look at the ACF, the autocorrelation function, again the first value is 1, but there's no indication here of how I can pick what order of AR process I have over here. If I look at the partial autocorrelations, the first, second, third, fourth are significant. Not the fifth. The fifth is actually quite small for some reason, but maybe the sixth as well. But I would actually ignore everything beyond, say, 4 or so here. So while I've got actually an AR5 process here, by looking at the partial autocorrelation function, it looks like an AR4 process. Now, when I start modeling data here, looking at these 4 plots over here, we do know that we always look for a simpler and smaller model. The larger the model, the more complicated it is to interpret that, and of course it's more complex to control the thing if that's your wish as well, and prediction as well. So we go for smaller models. Here it looks like AR4 is the model we should be trying to start off with. Anyway, that comes in the next part when you start looking at this model itself. Now, the other thing we looking at is this called the moving average process. And we shall look at that in the next lecture, and that's for next week. This is enough for 1 week, because we're playing with these data sets in the lab, plotting them out, fitting some models, and that'll be enough for 1 day. Thank you. Bye.